Right now, as you read this sentence, something impossible is happening inside your body. Electrons in your neurons are making decisions based on events that have not occurred yet. Photons striking your retina are being influenced by measurements that will happen in the future. The very atoms that constitute your being are operating in a realm where the distinction between past and future does not exist. This is not mysticism. This is not philosophy. This is the experimentally verified reality of quantum mechanics, confirmed in laboratories around the world over the past 4 decades. In 2012, physicists at the University of Vienna conducted an experiment that should have been impossible. They demonstrated that the state of a photon could be determined by a measurement made after that photon had already been detected and destroyed. The future was reaching back through time to shape the present. In 2015, a team at the Australian National University replicated and extended these results. They showed that particles exist in a state of quantum indeterminacy until an observation is made, and that observation can be made in what we would normally call the future. But here is what truly shatters our intuitions. The fundamental equations of physics, the laws that govern every particle in the universe, do not distinguish between forward and backward time. Play a video of atoms interacting, and a physicist cannot tell whether you are running it forward or in reverse. At the deepest level of reality, time has no arrow. So why does your coffee cool down but never spontaneously heat up? Why do you remember yesterday but not tomorrow? Why does glass shatter but never unshatter? The answer will force you to question everything you believe about the nature of time, causality, and reality itself. Because the arrow of time that governs your life may be nothing more than a cosmic accident, an illusion created by the particular conditions of our universe's birth. A statistical artifact that exists in your perception, but not in the underlying physics. What if the future is just as fixed as the past? What if the past is just as changeable as the future? What if the flow of time you experience every moment is the greatest deception reality has ever pulled on conscious beings? Today, we will journey from the equations of Ludwig Boltzmann to the quantum laboratories of Vienna and Canberra. We will examine experiments that seem to violate causality and theories that explain why they do not. Not really. We will confront the possibility that the time you think you understand is nothing like the time that actually exists. By the end, you will never look at a clock the same way again. Let us begin with the most disturbing fact in all of physics. Write down the fundamental equations that govern reality. Newton's laws of motion, Maxwell's equations of electromagnetism, Einstein's field equations of general relativity, Schrödinger's equation of quantum mechanics, the standard model of particle physics. Now perform a simple mathematical operation. Replace every instance of the time variable t with negative t. Run time backward. What happens to the equations? Nothing. They remain valid. Every solution that works forward in time also works backward in time. The mathematics does not care which direction you choose. This is called time reversal symmetry, and it is one of the most profound and troubling features of fundamental physics. The laws of nature, as we understand them, treat past and future as mathematically equivalent. Consider what this means. If you could film the motion of atoms in a gas and play the film backward, the reversed motion would be perfectly consistent with the laws of physics. Each collision, each trajectory, each exchange of momentum would obey Newton's laws exactly. The same is true for electromagnetic waves. A wave expanding outward from a source is physically identical, in terms of Maxwell's equations, to a wave contracting inward toward a sink. The equations permit both. Even quantum mechanics, for all its strangeness, respects time symmetry in its fundamental form. The Schrödinger equation that governs wave function evolution is symmetric under time reversal, when properly understood. If the laws of physics do not distinguish past from future, why do we? The answer comes from an unlikely source: a depressed Austrian physicist in the late 19th century who would eventually take his own life. Ludwig Boltzmann was born in Vienna in 1844. He dedicated his career to understanding the relationship between the microscopic world of atoms and the macroscopic world of everyday experience. His work would revolutionize physics, but it brought him only misery in his lifetime. Boltzmann's great insight concerned entropy, a quantity that measures the disorder or randomness of a system. He showed that the second law of thermodynamics, the law that states entropy always increases, is not a fundamental law at all. It is a statistical consequence of the arrangement of atoms. Consider a box divided in half by a partition. On one side, a gas. On the other side, vacuum. Remove the partition, and the gas expands to fill the entire box. This is irreversible. You never see a gas spontaneously compress itself into half the available space. But why? Boltzmann realized that the answer lies in counting. There are vastly more ways for gas molecules to be spread throughout the box than to be concentrated in one half. When you remove the partition, the gas is not pushed into the other half by any force. It simply explores all possible configurations, and most configurations have molecules everywhere. The second law of thermodynamics is not a law of physics. It is a law of statistics. Entropy increases because there are more high-entropy states than low-entropy states, and systems naturally evolve toward more probable configurations. But here is where the mystery deepens. Boltzmann's explanation accounts for why entropy increases toward the future. But remember, the underlying physics is time-symmetric. If we can explain entropy increase toward the future statistically, the same statistics should predict entropy increase toward the past. Think about it carefully. You know the current state of a glass of water with ice cubes. Using Boltzmann's reasoning, the most probable future state is one where the ice has melted and the water has reached a uniform temperature. More entropy. But the same reasoning, applied in the reverse time direction, suggests that the most probable past state is also one of higher entropy. The statistics predict that the ice cube should have spontaneously formed from warm water, which contradicts our memories and all of history. This is called Loschmidt's paradox, named after Joseph Loschmidt, a colleague of Boltzmann who raised the objection. If the fundamental laws are time-symmetric, and if statistical reasoning explains the arrow of time, why does the arrow point in only one direction? Boltzmann spent years wrestling with this problem. The answer he eventually proposed was radical and remains controversial to this day. The arrow of time, Boltzmann suggested, is not a feature of the laws of physics. It is a feature of the initial conditions of the universe. Let me explain what this means with an analogy. Imagine you walk into a room and see a completed jigsaw puzzle on a table. You might reasonably assume that someone assembled it, starting from scattered pieces and ending with the completed image. But the laws of physics permit the reverse process. A completed puzzle could spontaneously disassemble, with pieces jumping apart into a scattered configuration. Nothing in Newton's laws forbids this. Why does the first scenario seem natural and the second absurd? Because of the initial conditions. Puzzles start scattered and become assembled by human effort. This is a fact about how puzzles typically originate, not a fact about the laws governing puzzle pieces. Boltzmann proposed that the entire universe is analogous to a puzzle. The arrow of time exists because the universe started in an extraordinarily low entropy state, a state of extreme order from which entropy could only increase. The Big Bang was, in a thermodynamic sense, an incredibly improbable configuration. If you accept this, the arrow of time is not fundamental. It is contingent. In a universe that started differently, or in a sufficiently isolated region of our universe, time could flow the other direction. Entropy would decrease. Effects would precede causes. Memory would work in reverse. This is not science fiction. This is the standard explanation for the arrow of time accepted by most physicists today. Time's direction is an accident of cosmic history, not a law of nature. But the situation becomes even stranger when we examine quantum mechanics. In the classical world of Newton and Boltzmann, time symmetry is exact but hidden by statistics. In the quantum world, time symmetry takes on new and bizarre forms. The fundamental theorem is called CPT symmetry. It states that the laws of physics are invariant under the combined operations of charge conjugation, replacing particles with antiparticles, parity inversion, flipping space to its mirror image, and time reversal. This theorem is not optional. It is a mathematical consequence of the basic structure of quantum field theory, the framework underlying all of modern particle physics. Any theory consistent with special relativity and quantum mechanics must respect CPT symmetry. What does this mean in practice? It means that if you take any physical process, replace all particles with their antiparticles, reflect space, and run time backward, you get a process that is equally valid according to the laws of physics. The mirror-reversed, antiparticle, time-reversed version of our universe would obey exactly the same laws as our universe. In 1956, physicists discovered that parity alone is not conserved in certain weak nuclear interactions. This was a shock, and it earned Tsung-Dao Lee and Chen-Ning Yang the Nobel Prize. But CPT symmetry remained intact. In 1964, James Cronin and Val Fitch discovered that the combination of charge conjugation and parity, CP, is also violated in certain processes involving kaons. Another shock, another Nobel Prize in 1980. But again, CPT symmetry held. Every experiment ever performed has confirmed CPT symmetry to extraordinary precision. The combined operation that includes time reversal is an exact symmetry of nature. Time reversal is woven into the fabric of reality at the most fundamental level. Now we come to the experiments that seem to violate causality itself. In 1978, physicist John Wheeler proposed a thought experiment called the delayed choice experiment. It was designed to probe the strange relationship between measurement and reality in quantum mechanics. Here is the setup. A single photon is sent toward a beam splitter, a half-silvered mirror that has a 50% chance of reflecting the photon and a 50% chance of transmitting it. If reflected, the photon travels one path. If transmitted, it travels another. At the end of each path is a detector. In normal operation, you would see the photon arrive at one detector or the other, randomly, with equal probability. The photon behaves like a particle, taking one path or the other. But Wheeler proposed adding a second beam splitter at the point where the two paths converge. If this second splitter is present, the two paths can interfere with each other. Depending on the precise lengths of the paths, this interference can direct the photon to one detector with certainty. The photon behaves like a wave, traveling both paths simultaneously. Particle or wave? In quantum mechanics, this depends on the experimental setup. But here is Wheeler's twist. What if you decide whether to insert the second beam splitter after the photon has already passed the first splitter? At the moment the photon encounters the first beam splitter, it must somehow commit to being a particle or a wave. But the choice of whether to test for particle behavior or wave behavior has not yet been made. How can the photon know what to do? Wheeler's proposal remained a thought experiment for years. The technology to test it did not exist. But in 1984, physicists at the University of Maryland conducted the first delayed choice experiments. The results were exactly as quantum mechanics predicted, and deeply disturbing. The photon's behavior at the first beam splitter depends on whether the second beam splitter is present. But the decision about the second splitter is made after the photon has already passed the first splitter. The future measurement determines the past behavior. Or does it? The interpretation of delayed choice experiments remains contentious. Some physicists argue that no information actually travels backward in time. The correlations we observe can be explained without invoking retrocausality, through careful attention to what we mean by a photon's properties before measurement. But other physicists take the experiments at face value. They argue that the quantum world genuinely does not respect our intuitions about the order of cause and effect. The future and the past are entangled in ways that classical physics never anticipated. In 2007, a team led by Alain Aspect in France performed an even more dramatic version of the experiment using entangled photons. They showed that correlations between distant measurements can depend on choices made after the photons are already in flight. The results confirmed quantum mechanics, but deepened the mystery. Let me describe the 2012 Vienna experiment in more detail, because it represents the current frontier of these investigations. Physicists Xiaosong Ma, Johannes Koffler, and Anton Zeilinger, along with colleagues at the Austrian Academy of Sciences, performed what they called quantum delayed choice entanglement swapping. The setup is complex, but the key result is simple and stunning. Two photons are created that are not initially entangled with each other. They are detected and destroyed. Only afterward is a measurement made on two other photons that determines, retroactively, whether the first two photons were entangled or not. Read that again. The properties of particles that have already been detected and no longer exist are determined by a measurement made in the future. The experiment was published in Nature Physics and has been replicated multiple times. It is not controversial in terms of the results. The data are clear. What remains controversial is what the results mean. Zeilinger, one of the world's leading experts in quantum foundations, has stated that these experiments show that quantum mechanics forces us to abandon certain intuitions about reality. Whether we say the future affects the past, or that properties do not exist until measured, the classical notion of a fixed past is not compatible with the quantum world. How should we understand these results? One interpretation is called retrocausality. On this view, causes can genuinely precede effects in time. The future measurement causes the past state. Time is not a one-way street. This interpretation has serious defenders among physicists. Hugh Price, a philosopher of physics at Cambridge University, has argued that retrocausality may be necessary to understand quantum mechanics. Physicist Yakir Aharonov and colleagues have developed the two-state vector formalism, which explicitly incorporates influences from both past and future in quantum predictions. The advantage of retrocausality is that it can explain quantum correlations without invoking faster-than-light influences. If the future can affect the past, then distant particles can be coordinated without any signal passing between them. The correlation is established across time, not across space. But retrocausality faces serious objections. If the future can affect the past, why can we not send messages backward in time? Why can we not create paradoxes? The answer, retrocausalists claim, is that the backward influences are always hidden within quantum indeterminacy. They affect probabilities, not definite outcomes. They cannot be used to transmit usable information. This is a delicate balance. The universe seems to permit backward causation at the quantum level, while forbidding it at the macroscopic level. The same statistical effects that create the arrow of time may mask the time-symmetric nature of fundamental physics. Another interpretation is even more radical. It denies that the past is fixed at all. On this view, called the block universe or eternalism, all of time exists equally. The past, present, and future are all real, in the same way that distant locations in space are real. The flow of time is an illusion, a feature of how conscious beings experience the static, four-dimensional structure of space-time. Einstein himself leaned toward this view. After the death of his close friend Michel Besso, Einstein wrote in a letter of condolence that the distinction between past, present, and future is only a stubbornly persistent illusion. Besso had simply departed from this world a little ahead of Einstein. They both existed eternally in the block of space-time. If the block universe is correct, the delayed choice experiments are not surprising at all. There is no past being affected by a future cause. There is simply a four-dimensional pattern of events, and what we call cause and effect are just correlations within that pattern. The pattern is consistent, and that is all physics requires. But this view has its own disturbing implications. If the future already exists, then free will may be an illusion. Your choices are already made, already present in the block universe. waiting for your consciousness to arrive at them. You are not deciding your future, you are discovering it. Let us take a step back and consider what we have learned so far. The fundamental laws of physics are symmetric under time reversal. They do not distinguish past from future. This is not speculation. It is mathematical fact, confirmed by every experiment. The arrow of time we experience, the asymmetry between past and future, arises from special initial conditions at the Big Bang, not from the laws themselves. In principle, time could flow either way. Our experience of one-way time is contingent, not necessary. Quantum mechanics adds further complications. Experiments show correlations that seem to require influences from the future, or at minimum, show that the past is not fixed until measured. The interpretation remains disputed, but the data are solid. What does this mean for you, sitting there, reading these words? It means the time you think you understand, the time of clocks and calendars, of memories and anticipation, may bear little resemblance to the time that actually exists. The flow you experience may be a kind of user interface, a simplified representation that evolution gave you because it was useful, not because it is true. Part 2. The Arrow of Entropy. We must now examine more carefully how the arrow of time emerges from time-symmetric physics. This is the heart of the mystery, and it involves some of the deepest questions in science. Return to Boltzmann's insight. Entropy increases toward the future because there are more high-entropy states than low-entropy states. Systems naturally evolve toward more probable configurations. This explains why your coffee cools, why ice melts, why glass shatters. But remember Loschmidt's paradox. The same reasoning, applied in reverse, predicts that entropy should also increase toward the past. Yet it does not. The past, as we remember it, and as records indicate, had lower entropy than the present. Boltzmann's solution was to invoke special initial conditions. The universe started in a low entropy state. From that starting point, entropy has been increasing ever since. The arrow of time points from the low entropy past toward the high entropy future. This explanation works, but it raises a deeper question. Why did the universe start with low entropy? What set up the special initial conditions that give us our arrow of time? The Big Bang was, by any measure, an extraordinarily special state. 14 billion years ago, give or take, the universe was compressed into a hot, dense plasma of nearly uniform temperature and density. Particles were distributed almost perfectly evenly across space. There were no galaxies, no stars, no planets. Just a smooth sea of radiation and matter. This seems like chaos, does it not? High entropy? Maximum disorder? Actually, no. This is one of the most counterintuitive aspects of cosmology. The early universe had very low entropy, precisely because it was so uniform. The reason is gravity. In a system dominated by gravity, uniform distributions are not equilibrium states. They are unstable. Gravity amplifies tiny fluctuations, pulling matter together into clumps. Stars form, then galaxies, then clusters of galaxies. This clumping represents an increase in entropy. Wait, how can clumping increase entropy? It seems like it should be the reverse. Clumped matter looks more organized than uniformly distributed matter. The answer is that entropy is not about visible order. It is about the number of microscopic configurations consistent with a macroscopic state. When matter clumps under gravity, it releases energy, typically as radiation. That radiation carries away enormous amounts of entropy. The total entropy of matter plus radiation increases, even though the matter becomes more concentrated. Black holes are the ultimate example. A black hole represents the maximum entropy that can be packed into a given region of space. When matter falls into a black hole, entropy increases dramatically. The smooth, uniform early universe was as far from equilibrium as possible, given gravity. So the low entropy initial conditions of the Big Bang are not that it was hot and dense. It is that it was hot, dense, and smooth. The uniformity was the special part. and we still do not understand why the universe started that way. This is known as the past hypothesis. It is the assumption, built into our physical theories, that the universe began in a state of extremely low entropy. The past hypothesis is not derived from the laws of physics. The laws are time-symmetric. They do not prefer low-entropy beginnings over low-entropy endings. The past hypothesis is an additional assumption added to explain the observed arrow of time. But is it really an explanation? Or is it just restating the mystery? Philosopher David Albert of Columbia University has argued that the past hypothesis is a genuine addition to our physical theory, as fundamental as the laws of motion themselves. Without it, statistical mechanics cannot explain the phenomena we observe. With it, everything falls into place. But physicist Sean Carroll of Johns Hopkins University and others have pushed further. Why should we accept an unexplained assumption about initial conditions? Should we not try to derive the low-entropy beginning from deeper principles? Carroll has proposed that the universe may be much larger than we observe, perhaps infinitely large in time. Our Big Bang may be just one event in an eternal cosmos, a fluctuation that happened to produce a low-entropy region. Time may flow in different directions in different parts of this larger structure. Our arrow of time may be local, not cosmic. This is speculative, but it illustrates the depth of the problem. The arrow of time is not explained by known physics. It is assumed by known physics, and that assumption cries out for deeper understanding. Let us consider what the world would be like if the arrow of time pointed the other direction. In a time-reversed universe, entropy would decrease toward what we call the future. Broken eggs would reassemble. Dead organisms would come back to life. Memories would be of future events, not past ones. Actually, that last statement is tricky. If you lived in a time-reversed universe, you would not experience time as flowing backward. You would experience it as flowing forward, toward lower entropy. Your memories would still feel like they are of the past, even though an external observer from our universe would say they are of the future. This is because memory itself is a thermodynamic phenomenon. Creating a memory requires energy dissipation and entropy increase. In a time-reversed universe, the process of memory formation would be reversed. You would forget the future and remember the past, where past and future are defined relative to the direction of entropy decrease. This suggests something profound. The direction of time that we experience is not arbitrary. It is locked to the direction of entropy increase. Conscious experience, memory, causation, all of these are aspects of the thermodynamic arrow. If the arrow reversed, so would our experience. We would not notice anything strange. We would simply live our lives in the opposite temporal direction, convinced that our past is behind us and our future ahead. But here is a puzzle that has troubled physicists for decades. The thermodynamic arrow of time, based on entropy, seems distinct from other arrows of time in physics. The radiative arrow describes why electromagnetic waves expand outward from sources rather than contracting inward. The cosmological arrow describes why the universe expands rather than contracts. The quantum arrow describes the apparent irreversibility of wave function collapse. Are these arrows all the same? Are they different? Why do they all point in the same direction? The consensus, though not universal, is that all these arrows derive ultimately from the thermodynamic arrow, and the thermodynamic arrow derives from the low-entropy initial conditions of the Big Bang. Radiation expands outward because we are surrounded by absorbers, not emitters, of radiation. This asymmetry traces back to the thermodynamic conditions of the universe. The cosmological arrow, the expansion of the universe, is directly related to the initial conditions that established low entropy. The quantum arrow is more controversial. Some physicists believe wave function collapse is a real, irreversible process that adds a genuine arrow of time to physics. Others believe collapse is an illusion, an artifact of how observers interact with quantum systems, and that the underlying physics remains time-symmetric. If the latter view is correct, then all arrows of time may reduce to thermodynamics, and thermodynamics reduces to initial conditions. Time's arrow is not woven into the laws of nature. It is painted on by the universe's particular history. Let me tell you about an experiment that illustrates just how contingent the arrow of time really is. In 2002, physicists at IBM's Almaden Research Center in California performed an experiment in nuclear magnetic resonance. They took a collection of nuclear spins, set them in a particular configuration, and let them evolve freely. As expected, the spins became disordered over time. Entropy increased. This is the normal thermodynamic arrow at work. But then they did something remarkable. Using precisely timed radio pulses, they reversed the evolution. They effectively ran time backward for the spins, and the spins returned to their original, ordered configuration. Entropy decreased. The arrow of time for this isolated system pointed backward. This is not magic. It is physics. The fundamental laws are time-symmetric, so any evolution can be reversed if you have sufficient control over the system. What makes the arrow of time robust in everyday situations is not fundamental physics. It is the practical impossibility of reversing the evolution of trillions of particles interacting with an environment. But in a sufficiently isolated, sufficiently simple system, the arrow can point either way. The experiment demonstrates that time's direction is not a fundamental feature of reality. It is an emergent phenomenon, arising from complexity and initial conditions. This brings us to a profound question about the nature of time itself. Is time real? Does it flow? Or is the flow of time an illusion, a construct of conscious experience? Physicists and philosophers have debated this for centuries. The block universe view, which we discussed earlier, holds that all times are equally real. The flow of time is not a feature of the universe, but a feature of how we experience it. On this view, asking what time it is now is like asking what place is here. The answer depends on the questioner's location. There is no objective now, any more than there is an objective here. Each observer has their own present, defined by their position in space-time. But if the flow of time is not real, what is happening when you experience time passing? What creates the sensation of nowness, of the present moment continually updating? One possibility is that the experience of time flow is related to entropy increase. As entropy increases, systems acquire records of the past, but not the future. Brains are such systems. The asymmetry of entropy creates an asymmetry of memory, and that asymmetry feels like the flow of time. On this view, you do not experience time flowing because time actually flows. You experience time flowing because you are a thermodynamic system embedded in a universe with a particular entropy gradient. The sensation is real, but its interpretation is wrong. This is difficult to accept. The flow of time is perhaps the most immediate and undeniable feature of experience. To be told it is an illusion seems absurd. But physics has taught us to be humble about our intuitions. We intuit that the Earth is stationary and the sun moves, but we are wrong. We intuit that space is flat and uniform, but we are wrong. We intuit that particles have definite positions and velocities, but we are wrong. Why should our intuition about time be reliable when so many other intuitions have failed? The experience of time flow may be similar to the experience of color. Colors seem to be properties of objects out there in the world. But physics tells us that color is a feature of how our brains process certain wavelengths of light. The redness of a rose is not in the rose, it is in your brain. Perhaps the flow of time is similar. It seems to be a feature of the world, out there in reality. But it may be a feature of how brains process information in the direction of entropy increase. The flow of time is not in time, it is in your brain. Let us summarize where we have arrived. The fundamental laws of physics are time-symmetric. They do not distinguish past from future. This is established mathematical fact. The arrow of time we experience arises from special initial conditions, specifically the low entropy state of the early universe. This is the past hypothesis, an assumption added to physics rather than derived from it. Entropy increase creates the thermodynamic arrow, which likely underlies all other arrows of time, including the psychological arrow of memory and experience. The flow of time may not be a feature of physical reality, but a feature of how conscious beings process information in an entropic universe. And quantum mechanics adds further complications, with experiments suggesting that the past may not be fixed until measured, and that correlations can depend on future choices. What does this mean for you? Part 3. The quantum erasure of time. We have seen that classical physics is time-symmetric, and that the arrow of time emerges from initial conditions. But quantum mechanics takes us further into strange territory. It suggests that the very concept of a definite past may be problematic. Let me describe one of the most disturbing experiments in the history of physics. It is called the quantum eraser, and it was first proposed by Marlin Scully and Kai Druhl in 1982. Start with the classic double-slit experiment. A beam of particles, say photons, is directed at a barrier with two slits. Behind the barrier is a detection screen. If you simply let the photons through without any attempt to determine which slit each photon passes through, you see an interference pattern on the screen. Bright and dark bands, characteristic of wave behavior. The photons seem to pass through both slits simultaneously and interfere with themselves. But if you add detectors at the slits to determine which path each photon takes, the interference pattern disappears. You see two bands, corresponding to the two slits. The photons now behave like particles, each passing through one slit or the other. This is the standard quantum mystery. Measurement affects behavior. Observation determines reality. The quantum eraser adds a twist. What if you detect which path information, but then erase it before looking at the results? Here is how it works in detail. Send photons toward the double slit. At each slit, place a device that marks the photon in some way, encoding which slit it passed through. This marking destroys the interference pattern, just as direct observation would. But now, before the photon reaches the detection screen, send the marking information to a separate detector. At this detector, you have a choice. You can measure the marking and learn which slit the photon passed through. Or, you can perform a different measurement that erases the which path information without revealing it. If you measure the marking, no interference. If you erase the marking, interference returns. But here is the truly strange part. The photon has already been detected on the screen before you decide whether to measure or erase the marking information. The pattern on the screen, particle-like or wave-like, depends on a choice you make afterward. Does this mean the future affects the past? The quantum eraser experiments have been performed many times with consistent results. The most famous was conducted by Yoon Ho Kim, R.U., S.P. Kulik, Y.H. Shi, and Marlin Scully in 1999 at the University of Maryland. Their results confirmed the theory exactly. The interference pattern, or lack thereof, depended on measurements made after the photons had already been detected. Importantly, you cannot use this effect to send signals backward in time. If you look at the screen without knowing whether the marking was measured or erased, you see no interference pattern. It is only when you sort the photons according to the later measurement that you find interference in some subgroups and no interference in others. The pattern is there, hidden in the correlations, but extracting it requires knowing the future measurement result. Information does not travel backward. Correlations do. Or do they? The interpretation remains hotly debated. Some physicists accept these results as evidence that quantum mechanics is genuinely retrocausal. The future measurement does affect the past behavior, but in a subtle way that cannot be exploited to send messages. Physicist John Cramer of the University of Washington developed the transactional interpretation of quantum mechanics specifically to accommodate retrocausality. On his view, quantum events involve handshakes between waves traveling forward in time and waves traveling backward in time. The transaction is completed when both waves agree, establishing the outcome. Other physicists reject retrocausality entirely. They argue that the quantum eraser can be explained without backward causation if we properly understand what quantum states represent. The photon at the screen never had a definite which path property to be affected. The correlations we observe are just features of the entangled quantum state, which exists outside of our intuitive notions of time ordering. This is the many worlds interpretation, developed by Hugh Everett in 1957. On this view, all possible outcomes of quantum measurements actually occur in separate branches of reality. There is no collapse, no backward causation, just a vast tree of parallel worlds encompassing all possibilities. But even in many worlds, the fundamental time symmetry remains. The branching structure does not prefer a direction of time. The appearance of time flow is still an artifact of how observers experience the branching structure, not a fundamental feature of reality. Let me describe one more experiment that pushes these ideas to their limits. In 2015, Andrew Truscott and colleagues at the Australian National University performed a delayed choice experiment with atoms rather than photons. Atoms are more massive, more particle-like, more intuitively real. If delayed choice effects work with atoms, the implications are harder to dismiss. They created a Bose-Einstein condensate, a cloud of atoms cooled to near absolute zero where quantum effects dominate. They dropped pairs of atoms and let them fall, then used laser pulses to recombine them after they had separated. The key result was the same as with photons. The behavior of the atoms at an earlier time depended on a measurement choice made at a later time. Atoms that had already separated and fallen could be made to interfere or not interfere depending on future decisions. Truscott summarized the result bluntly. At the quantum level, reality does not exist until we measure it, and measurement in the future can affect what reality existed in the past. This is not philosophy. It is experimental physics, published in Nature Physics, replicated and confirmed. What should we conclude from these experiments? The conservative conclusion is that quantum mechanics forces us to revise our notion of physical properties. Particles do not have definite positions, momenta, or which path properties until measured. The past is not determinate in the way we intuitively assume. The radical conclusion is that causation itself is not one-directional. The future can influence the past, at least at the quantum level. The classical notion of a fixed past being causally prior to an open future is not compatible with quantum reality. Both conclusions are uncomfortable. Both force us to abandon intuitions that seem undeniable. Perhaps the deepest lesson is that time, as we experience it, is not the time of fundamental physics. Our intuitive picture of a flowing present, separating a fixed past from an open future, may be a psychological construct rather than a physical reality. The experiments do not tell us what time is, they tell us what time is not. And what time is not is what we always thought it was. Part 4. The Block Universe and Eternalism. We have arrived at one of the oldest and most profound questions in philosophy. Is time real? Does the present moment have a special status? Or is the flow of time an illusion, with past, present, and future all equally real? The view that all times are equally real is called eternalism, or the block universe theory. On this view, the universe is a four-dimensional block of space-time. Events do not come into being and pass away. They simply exist at their locations in the block. You exist at many points in this block, from your birth to your death. None of these versions of you is more real than the others. They are all equally present in the eternal structure of space-time. The flow of time, on this view, is not a feature of the universe. It is a feature of conscious experience within the universe. Each moment of your experience includes memories of earlier moments and anticipations of later moments. This asymmetry creates the sensation of time flowing. But the sensation is internal to you, not external in the world. Einstein, as we mentioned, leaned toward this view. His theory of special relativity strongly supports it. In special relativity, there is no objective simultaneity. Two events that are simultaneous for one observer may occur at different times for another observer moving relative to the first. There is no universal now cutting across the universe. If there is no universal now, what does it mean to say the present is special? Special relative to whom? Any answer privileges one observer's perspective over another's, which violates the principle of relativity. The block universe avoids this problem by treating all times equally. There is no universal now because no time is privileged. Each observer has their own present, defined by their world line through spacetime. These presents are all equally real within the block. Physicist Hermann Minkowski, who developed the mathematical framework of spacetime shortly after Einstein's 1905 paper, declared that space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. Spacetime is the reality. Space and time, as separate entities, are observer-dependent projections. But the block universe faces serious objections. The most visceral objection is phenomenological. The flow of time is the most immediate feature of experience. To declare it an illusion seems to contradict the very evidence of consciousness. How can the illusion of flow arise in a static block? Block universe defenders have responses. The experience of flow does not require actual flow in the world. It requires only that each time slice of your brain contains memories of earlier time slices. The experience is real, as an experience, even if its interpretation is mistaken. This is similar to how the experience of color is real, even though colors are not objective properties of the external world. You really do experience red. That experience exists. But it does not follow that redness is out there in the world, independent of your perception. Time flow might be the same. You really do experience time passing. That experience exists at every moment in the block. But it does not follow that time actually passes in any objective sense. A deeper objection concerns change and causation. In the block universe, nothing changes in a fundamental sense. All events simply are, eternally. But our concept of change seems essential to understanding the world. How can there be change without time flow? Block universe defenders distinguish between change within the block and change of the block. Events at one location in the block differ from events at other locations. This is change within the block. A ball is in one position at one time and another position at another time. The ball has changed across the time dimension. But the block itself does not change. It does not come into being or pass away. It simply exists, eternally, in its four-dimensional totality. This distinction may seem like verbal trickery, but it captures something important. The laws of physics describe how quantities vary across spacetime, not how spacetime itself changes. Change is variation along the time dimension, not motion through time. Causation is trickier. We intuitively think of causes as bringing about effects, making them happen. The match striking causes the flame. The cause is active, productive, efficacious. But in the block universe, both the striking and the flame simply exist at their locations. Neither produces the other in any dynamic sense. They are correlated features of the block. Some philosophers find this implication disturbing. It seems to reduce causation to mere correlation, stripping it of its productive force. Others embrace the reduction. Causation, they argue, just is certain patterns of correlation in spacetime. There is no additional ingredient of production or necessitation. The striking and flame are correlated in systematic ways, and that is all causation ever was. This debate connects to deep issues in the philosophy of science. Is causation fundamental, or is it reducible to patterns of events? The block universe strongly suggests the latter. There is another version of the block universe that tries to accommodate our intuitions about the open future. It is called the growing block theory. On this view, the past and present are real, but the future is not. The block is not static, but growing, with new moments being added as time passes. The present is the edge of existence, the boundary between what is and what is not yet. This view preserves some of our intuitions. The past is fixed and real, as we believe. The future is open and unreal, as we believe. Time genuinely flows, in the sense that the block genuinely grows. But the growing block faces its own problems. What makes the present special? Why is one moment the edge of the block rather than another? And how fast does the block grow? These questions have no clear answers. Moreover, special relativity poses the same challenge to the growing block as to presentism. If there is no universal simultaneity, which moment is the edge of the block? Different observers would disagree. Most physicists who accept the block universe accept the eternal version. The entire four-dimensional structure exists tenselessly. The present is not special except relative to an observer's location within the block. Let us consider the implications for free will. If the block universe is correct, then your future is as fixed as your past. The decisions you have not yet made already exist at their locations in space-time. You will experience them as choices when you reach those moments. But from the block perspective, they are already there. Does this mean free will is an illusion? Not necessarily. Compatibilists argue that free will is compatible with determinism. What matters is not whether your choices are determined, but whether they are determined by the right kinds of factors, namely your own desires, beliefs, and deliberations. On this view, you have free will if you act according to your own reasons. The fact that those reasons, and the actions they produce, are fixed in the block does not undermine their status as yours. You are still the one doing the choosing, even if the choice is eternally present in space-time. Incompatibilists reject this. They argue that genuine free will requires an open future, the ability to do otherwise. If the future is fixed, then you could not have done otherwise, and your will was not truly free. The debate is ancient and unresolved. But the block universe interpretation of physics lends support to the compatibilist side. If modern physics suggests the future is as real as the past, then our notions of freedom must adapt accordingly. There is one more perspective I want to share before we move on. Some physicists and philosophers have argued that consciousness itself is the key to understanding time. The flow of time, they suggest, is not an illusion, but a fundamental feature of conscious experience, one that physics cannot capture because physics abstracts away from consciousness. On this view, the block universe is a useful model for certain purposes, but incomplete. It describes the objective structure of space-time, but leaves out the subjective experience of time flow. A complete theory of reality would need to incorporate both. This is a minority view among physicists, but has serious defenders. Philosopher Tim Maudlin of New York University argues that the passage of time is a fundamental feature of reality that physics should accommodate, not explain away. Physicist Lee Smolin of the Perimeter Institute has argued that time is more fundamental than space, and that the future is genuinely open. The debate continues. But whatever the ultimate resolution, it is clear that our intuitive understanding of time is at best incomplete, and at worst, deeply mistaken. Physics has shown us a world far stranger than common sense suggests. Part 5. What physicists do not tell you. We have explored the time symmetry of fundamental physics, the statistical origin of entropy, the bizarre implications of quantum mechanics, and the block universe interpretation. But there are gaps in this picture, things physicists rarely discuss in public, controversies that remain unresolved. Let me share some of these hidden debates with you. The first uncomfortable truth is that we do not have a quantum theory of gravity. General relativity describes gravity as the curvature of space-time. It is a theory about the geometry of time itself. Quantum mechanics describes the behavior of matter at small scales. It is a theory where time plays a very different role, as a background parameter rather than a dynamic variable. When we try to combine these theories, disaster ensues. The mathematics breaks down. Infinities appear that cannot be removed. Our two best theories of physics are fundamentally incompatible. This matters for our understanding of time because the nature of time might be radically different in a true theory of quantum gravity. Some approaches, like loop quantum gravity developed by Abhay Ashtekar, Lee Smolin, and Carlo Rovelli, suggest that space-time itself is discrete at the smallest scales. Time might come in indivisible chunks, like frames of a film. The continuous flow of time might be an approximation that breaks down at the Planck scale, around 10 to the negative 43 seconds. Other approaches, like string theory, suggest extra dimensions of space and time that are hidden from our observation. Time might be more complex than we imagine, with multiple time dimensions, or time emerging from more fundamental structures. The honest answer is that we do not know what time is at the most fundamental level. Our theories break down precisely where we need them most. The nature of time remains one of the deepest unsolved problems in physics. The second uncomfortable truth concerns the measurement problem in quantum mechanics. We have discussed how quantum systems exist in superpositions until measured, and how measurement seems to determine reality retroactively. But what exactly is a measurement? When does the wave function collapse? What makes some interactions measurements and others not? These questions have no agreed-upon answers. Different interpretations of quantum mechanics give different responses, and there is no experimental way to distinguish between them. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg in the 1920s, treats measurement as a primitive concept. It does not explain what a measurement is. It simply postulates that measurements produce definite outcomes according to certain probabilities. The many-worlds interpretation, developed by Hugh Everett in 1957, eliminates collapse entirely. All possible outcomes occur in branching parallel realities. But this raises its own puzzles about probability and the nature of these parallel worlds. The pilot wave theory, developed by Louis de Broglie and later David Bohm, restores determinism by adding hidden variables. Particles have definite positions at all times, guided by a wave that evolves according to Schrödinger's equation. But this requires a preferred foliation of spacetime, a universal now, which conflicts with special relativity. Each interpretation has implications for the nature of time. Some preserve time symmetry, others break it. Some treat the past as fixed, others do not. The lack of consensus means we cannot be certain what quantum mechanics actually tells us about time. The third uncomfortable truth is that entropy might not always increase. The second law of thermodynamics, which says entropy always increases, is statistical rather than fundamental. It holds overwhelmingly in practice because high entropy states vastly outnumber low entropy states. But it is not absolutely certain. In principle, a system could spontaneously fluctuate to a lower entropy state. All the air molecules in your room could, by chance, collect in one corner, leaving you in a vacuum. The probability is unimaginably small, far less than 1 in 10 to the power of 10 to the power of 20. But it is not zero. Over sufficiently long timescales, even extremely improbable events become likely. If the universe lasts forever, entropy fluctuations will eventually occur. Regions of low entropy will spontaneously appear from thermal equilibrium. This has bizarre implications. It suggests that ordered structures, even brains with false memories, could pop into existence from chaos. These Boltzmann brains, as they are called, would have no history. Their memories would not correspond to any actual past. If Boltzmann brains are possible, and if the universe is eternal, then most observers in the universe might be Boltzmann brains rather than evolved beings like us. This is the Boltzmann brain paradox, and it remains unresolved. Some physicists argue that this paradox shows our cosmological models are incomplete. Others argue that it shows the universe cannot be eternal. Still others bite the bullet and accept that we might be Boltzmann brains. The arrow of time, which seems so robust, might be more fragile than we thought. The fourth uncomfortable truth is that time might not be fundamental. Several approaches to quantum gravity suggest that time emerges from more basic structures that are themselves timeless. In the Wheeler-DeWitt equation, formulated by John Wheeler and Bryce DeWitt in 1967, time does not appear at all. The equation describes the quantum state of the entire universe, and that state is static, unchanging. Time must emerge from within this timeless framework, perhaps through the relationships between subsystems. Carlo Rovelli has developed this idea further in his thermal time hypothesis. He suggests that what we perceive as time flow is actually a measure of our ignorance about the microscopic state of the universe. Time is not fundamental, but emergent, arising from thermodynamics rather than underlying it. Julian Barber, in his book The End of Time, argues even more radically that time does not exist at all. What we call time is just a way of describing correlations between configurations of matter. The universe is a collection of moments, each complete in itself, with no temporal ordering except what we impose through our descriptions. These ideas are speculative, but taken seriously by respected physicists. They suggest that our experience of time, however vivid, might not correspond to any fundamental feature of reality. The fifth uncomfortable truth concerns the experiments themselves. The delayed choice experiments we discussed are real and have been replicated, but their interpretation remains contested. Not all physicists agree that they demonstrate retrocausality or the indeterminacy of the past. Some argue that the experiments can be explained without any exotic metaphysics. The correlations we observe are just features of quantum entanglement, which does not involve any backward causation. The appearance of the future affecting the past is an artifact of how we describe the experiment, not a feature of reality. Others argue that the experiments are even stranger than usually presented. They suggest that the correlations reveal a fundamental non-locality in nature, where distant events are connected in ways that transcend our ordinary notions of space and time. The honest position is uncertainty. We do not know for certain what these experiments mean. Different interpretations remain viable, and new experiments continue to probe the boundaries of our understanding. Science is not a collection of fixed truths. It is an ongoing process of investigation, revision, and debate. The nature of time is among the most actively debated topics in contemporary physics. Let me tell you about a more recent experiment that has added fuel to these debates. In 2017, physicists at the University of Queensland in Australia performed what they called an indefinite causal order experiment. They created a quantum superposition not just of particle states, but of the order in which operations were performed. Imagine two operations, A and B. Normally, either A happens before B or B happens before A. Causality has a definite order. But in this experiment, the quantum system was placed in a superposition of both orders. A happened before B, and B happened before A, simultaneously. The results showed quantum interference between the two orderings. The system behaved as if both causal orders were real, with no definite fact about which came first. This is not the future affecting the past. It is stranger. It is the very notion of before and after being in superposition. Causal order itself becomes indefinite at the quantum level. The implications are still being worked out, but the experiment suggests that our intuitive notion of temporal order, of causes preceding effects in a definite sequence, may not apply at the fundamental level of reality. Part 6. Consciousness and the experience of time. We have focused so far on what physics tells us about time. But there is another dimension to the question, the subjective experience of time that each of us has from the inside. You know what it feels like for time to pass. You remember the past. You anticipate the future. You exist in a present moment that seems to move forward, dragging you along. This experience is undeniable, whatever physics might say about it. But what exactly is this experience? And how does it relate to the physical structure of time? Neuroscience has begun to investigate how the brain generates the experience of time. Different brain regions process different aspects of temporal experience. The cerebellum tracks short intervals on the scale of milliseconds, crucial for motor coordination and rhythm perception. The basal ganglia handle longer intervals of seconds to minutes, important for learning and reward. The prefrontal cortex integrates these signals and creates our conscious sense of duration. Damage to these regions produces characteristic distortions in time perception. Patients with cerebellar damage struggle with fine timing tasks. Patients with prefrontal damage have difficulty estimating durations and may experience time as fragmented or discontinuous. These findings suggest that our experience of time is constructed by the brain, not passively received from the world. The flow of time that seems so real might be a neural construct, as much a product of brain activity as color perception or emotional tone. Certain altered states of consciousness dramatically affect time perception. In extreme fear or crisis situations, people often report that time seemed to slow down. Soldiers in combat, victims of accidents, and athletes in critical moments describe experiencing seconds as stretching into minutes. Retrospectively, the events seem to have taken much longer than they actually did. Neuroscientist David Eagleman has studied this phenomenon experimentally. He dropped volunteers from a tower while they performed timing tasks. His findings suggest that time does not actually slow down during fear. Instead, memory becomes denser. More details are encoded per unit of time, and when recalled, this denser memory creates the impression of extended duration. This fits with the broader picture. Time experience is tied to memory and attention. When we attend closely to experience, we form richer memories, and richer memories seem to last longer in retrospect. The child's endless summer and the adult's vanishing years reflect differences in how much novelty and attention characterize each period. Psychedelic substances produce even more dramatic alterations in time perception. Users of psilocybin, LSD, and DMT commonly report experiences where time loses its normal structure. The past, present, and future may seem to merge. The sense of duration may disappear entirely. Users may feel they have accessed an eternal present or experienced what feels like hours in mere minutes. In 2020, researchers at Johns Hopkins University published a study on DMT experiences. A significant percentage of participants reported encounters with seemingly autonomous entities and experiences of timelessness. Many described their experience as more real than ordinary reality. What should we make of such reports? Skeptics dismiss them as hallucinations, mere artifacts of brain chemistry with no metaphysical significance. But others suggest they reveal something about consciousness itself, perhaps its capacity to operate outside the ordinary temporal framework. The philosopher Henri Bergson argued in the early 20th century that scientific time, the time of clocks and physics, is an abstraction. Real time, lived time, is experienced as continuous flow, as duration, which cannot be captured by mathematical description. Perhaps altered states reveal aspects of time experience that ordinary consciousness suppresses. Or perhaps they simply show how easily the brain's time-generating machinery can be disrupted. The interpretation remains open. Meditation traditions have long claimed that the experience of time can be fundamentally altered through practice. In Buddhist psychology, the sense of a continuous self moving through time is considered a construction, an illusion that causes suffering. Through meditation, practitioners aim to see through this illusion and experience reality directly, without the filter of ego and temporal narrative. Advanced meditators report experiences that seem to transcend ordinary time. They describe entering states where past and future dissolve, where only an eternal present remains. Some claim to experience what feels like simultaneous access to all times, or complete freedom from temporal ordering. Are these experiences veridical? Do they reveal something true about the nature of time? Or are they simply alterations in neural processing with no external validity? Neuroscientists have begun to study meditators with brain imaging technology. They find consistent changes in brain activity, including alterations in regions associated with time perception and self-reference. But the metaphysical interpretation of these changes remains contested. What is clear is that the ordinary experience of time flow is not fixed. It can be altered by brain damage, by drugs, by extreme situations, and by mental training. This suggests that time experience is constructed, not given. And what is constructed might be constructed differently than we assume. Let us connect these observations back to physics. If the block universe is correct, then the flow of time is not a feature of physical reality. Yet we undeniably experience time flow. How can this be? The answer, according to block universe defenders, is that the experience of flow exists within the block. Each moment of your experience is a slice of the four-dimensional block. That slice contains memories of earlier slices and anticipations of later slices. The asymmetry of memory creates the impression of flow. You do not experience time passing because time actually passes. You experience time passing because each moment of your existence includes the right kind of information to generate that impression. This is philosophically coherent, but deeply counterintuitive. It means the flow of time is a kind of illusion, though a very persistent one. Each moment contains the impression of flow, but the flow itself does not occur in any objective sense. Some philosophers find this view disturbing or even absurd. They argue that the flow of time is more certain than any physical theory. If physics implies that time does not flow, then so much the worse for physics. Others embrace the implication. They note that many features of experience have turned out to be illusory or constructed. The solidity of objects, the continuity of perception, the unity of self. Perhaps the flow of time is another such construction, and recognizing it as such brings us closer to the truth. There is another possibility worth considering. What if consciousness itself is the key to understanding time? What if the experience of flow is not an illusion, but a clue to physics we do not yet understand? Some physicists have suggested that consciousness plays a fundamental role in quantum mechanics. The observer seems to have a special status in quantum theory, collapsing wave functions and determining outcomes. Perhaps this role connects to the experience of time. Physicist Roger Penrose has proposed that consciousness arises from quantum processes in microtubules within neurons. These processes, he suggests, are linked to the fundamental structure of space-time. If correct, the experience of time flow might reflect genuine features of quantum gravity that we do not yet understand. Penrose's ideas are controversial and not widely accepted, but they illustrate that the relationship between consciousness and time is an active area of speculation. We do not know what a complete theory would look like. Perhaps the experience of time flow will eventually be explained as a neural construction within a block universe. Or perhaps it will point us toward new physics, where time is more fundamental than current theories suggest. The question remains genuinely open. Part 7. The two-state vector formalism. I want to return to physics and describe one more theoretical framework that takes the time symmetry of quantum mechanics seriously. In 1964, physicist Yakir Aharonov, along with Peter Bergman and Joel Leibowitz, proposed what is now called the two-state vector formalism. It is an interpretation of quantum mechanics that explicitly incorporates influences from both past and future. In standard quantum mechanics, we describe a system by its quantum state, which evolves forward in time according to Schrödinger's equation. Measurements collapse this state into definite outcomes. The formalism is temporally asymmetric, with the past determining probabilities for the future. The two-state vector formalism adds a second state, one that evolves backward in time from a future measurement. The complete description of a quantum system requires both states, one from the past and one from the future. The two states together determine what happens at intermediate times. This is not a philosophical interpretation imposed on the mathematics. It is a mathematical framework that makes novel predictions, predictions that differ from standard quantum mechanics in subtle ways. The most striking prediction involves what Aharonov calls weak measurements. A standard quantum measurement disturbs the system strongly, collapsing the wave function. A weak measurement disturbs the system only slightly, gaining limited information without full collapse. The mathematics of weak measurements in the two-state vector formalism predicts surprising results. One prediction is anomalous weak values. When certain combinations of initial and final states are prepared, the weak value of an observable can lie outside the normal range of eigenvalues. For example, a spin that can only be +1 or -1 might have a weak value of 100. This sounds impossible, but it has been confirmed experimentally. In 1988, Aharonov, David Albert, and Lev Weidman predicted anomalous weak values. In 1991, the first experimental confirmation came from Yakir Aharonov's group. Since then, numerous experiments have verified the predictions. What do anomalous weak values mean? On Aharonov's interpretation, they reveal the genuine influence of the future on the present. The final state, the future boundary condition, affects what happens at intermediate times. Time symmetry is not just mathematical, but physical. Critics argue that weak values can be understood without invoking backward causation. The anomalous values might be artifacts of the measurement procedure rather than features of reality. The debate continues. Aharonov has developed these ideas into a comprehensive worldview he calls the two-time interpretation. On this view, quantum mechanics is fundamentally symmetric in time. The apparent asymmetry we observe is contingent, arising from particular boundary conditions at both ends of time. Just as the past hypothesis explains the thermodynamic arrow, specific future conditions might be needed to explain quantum phenomena. This leads to a startling picture. The universe is not just constrained by its initial conditions at the Big Bang, it is also constrained by final conditions at some future boundary. Both ends of time shape what happens in between. Does this mean the future is fixed? Not necessarily. The future boundary conditions might be probabilistic rather than deterministic. Or they might apply only to the universe as a whole, leaving local events undetermined. The details are still being worked out. What is significant is that a serious physical framework exists where the future genuinely influences the past. This is not fringe speculation, but peer-reviewed physics published in major journals. The time symmetry of fundamental physics is being taken seriously in ways that have measurable consequences. Let me describe one more recent development that connects to these ideas. In 2012, Matthew Pusey, Jonathan Barrett, and Terry Rudolph published a theorem that has implications for the reality of quantum states. Known as the PBR theorem after its authors, it shows that under certain assumptions, quantum states cannot be merely epistemic, representing our knowledge. They must be ontic, representing something real. Why does this matter for time? Because if quantum states are real, then their time-symmetric evolution is real. The mathematical symmetry is not just a calculational convenience, but a feature of physical reality. The PBR theorem does not settle all debates about quantum interpretation. Its assumptions can be questioned. But it adds weight to the view that quantum mechanics describes something objectively real, and that something is fundamentally time-symmetric. Combined with the experimental results on delayed choice and weak measurements, a picture emerges where time symmetry is not merely formal, but substantive. The future may not cause the past in any straightforward sense, but the relationships between past and future are more intimate than classical physics suggested. Part 8. Living with Timeless Physics. We have covered a vast territory. We have seen that fundamental physics is time-symmetric, that the arrow of time arises from initial conditions, that quantum mechanics suggests the past may not be fixed until measured, and that the Bloch universe treats all times as equally real. How should we live with these discoveries? What do they mean for our daily experience, our hopes and fears, our sense of meaning? Let me begin by acknowledging the strangeness. Nothing in ordinary experience prepares us for what physics has revealed. We wake each morning with the conviction that yesterday is gone, that today is happening now, that tomorrow is yet to come. We plan, we remember, we anticipate. The flow of time is the backdrop against which all of life occurs. To be told that this flow might be an illusion, that the past and future are equally real, that causation might run both ways, is disorienting. It contradicts everything we feel, But physics has contradicted our feelings before. We feel that the Earth is stationary. We feel that solid objects are continuous. We feel that simultaneity is absolute. In each case, careful investigation revealed that our feelings were misleading. The nature of time may be the deepest case yet. Our intuitions here are more entrenched, more visceral, more tied to the very structure of consciousness. But entrenchment does not guarantee truth. One response is to distinguish levels of description. Physics describes the fundamental structure of reality. Psychology describes the structure of experience. These may not be the same. The flow of time might be real at the level of experience, even if absent at the level of fundamental physics. Just as color is real in experience but not in physics, time flow might be experiential rather than physical. On this view, there is no contradiction between physics and experience. Physics tells us about the underlying structure. Experience tells us about how that structure is processed by minds. Both are valid within their domains. This does not make time flow an illusion in any pejorative sense. Colors are not illusions just because they are not properties of light waves. They are real features of visual experience. Similarly, time flow is a real feature of temporal experience, even if physical time does not flow. Another response is practical. Even if the future is as real as the past, you still have to live. You still make decisions. You still face consequences. The metaphysics of time does not change the fact that you experience choosing and acting. The block universe, if true, does not imply fatalism. Your decisions are part of the block. They are fixed, yes, but they are still yours. You still deliberate, weigh options, and act according to your reasons. The eternality of the block does not remove your agency. It situates your agency within a larger structure. This is subtle but important. Learning that the future is fixed does not mean your efforts are pointless. Your efforts are part of what fixes the future. Without your deliberation and action, the future would be different. The block includes your contribution. So act as you would have acted anyway. Plan for the future. Cherish the past. Engage with the present. The metaphysics is interesting, but does not change what you need to do. A third response is philosophical. If all times are equally real, then everything that has ever happened or ever will happen exists eternally. The people you have loved exist, in their times, forever. The moments of joy and connection you have experienced are not lost. They are located in the block, as real as the present moment. This can be a source of comfort. Mortality takes on a different meaning if your life is an eternal structure rather than a fleeting process. You do not cease to exist when you die. You exist eternally at the times when you lived. Death is just the boundary of your existence in the temporal dimension, like birth is the other boundary. The philosopher Derek Parfit drew comfort from views like this. He argued that personal identity over time is less important than we think. What matters is psychological continuity and connection, not some metaphysical sameness of self. And if that is right, the eternality of the block provides a kind of immortality. This is not a proof of anything. It is a way of finding meaning in physics that might otherwise seem cold and impersonal. The block universe is not bleak. It is full, containing every moment that ever was or will be, all equally present in the structure of reality. But let me also acknowledge the discomfort. If the future is fixed, then suffering is fixed. Every tragedy that will occur is already there in the block. The horrors of history and the horrors yet to come exist eternally, alongside the joys. This can seem unbearable. We want to believe that the future is open, that we can make it better, that the worst is not inevitable. The block universe seems to remove this hope. But does it? The future being fixed does not mean it is fixed independently of our actions. The future is fixed because of what we do, not despite it. If we work to reduce suffering, that work is part of why the future contains less suffering than it otherwise would. The block universe is not fatalist. It does not imply that our efforts are pointless. It implies that our efforts are eternally present, eternally contributing to the shape of reality. This is not quite the open future we intuitively desire. But it is not the closed future of fatalism either. It is something in between, where actions matter even though outcomes are eternal. There is also the question of what physics might yet discover. We have emphasized that our current understanding is incomplete. Quantum gravity does not yet exist. The measurement problem is unsolved. Time might be emergent from more fundamental structures. Future physics might vindicate our intuitions. It might reveal that time genuinely flows, that the future is genuinely open, that consciousness plays a fundamental role in the structure of reality. We cannot know what future discoveries will bring, or future physics might deepen the mystery. It might reveal that time is even less like our intuitions than current theories suggest. It might show that the very concept of temporal order breaks down at some level. The honest response is humility. We know a lot, but we do not know everything. The nature of time remains one of the deepest mysteries in science. Whatever confidence we have should be provisional, open to revision as our understanding grows. Part 9. The meaning of memory. Let us explore one more aspect of time that is crucial to human experience: memory. Memory is the way we access the past. It is how we know there was a yesterday, how we recognize ourselves as continuous beings, how we learn and plan and connect with others. Without memory, there is no sense of time at all. But what is memory, physically? And how does it relate to the time symmetry of fundamental physics? Memory is, at its core, a record. It is a physical state that carries information about an earlier physical state. Your memories are encoded in the synaptic connections of your brain. When you remember your childhood home, certain patterns of neural activity are recreated, patterns that were established through experience and strengthened through repetition. This encoding process is thermodynamic. It requires energy. It produces heat. It increases entropy. Creating a memory is like writing a book or burning a candle. It leaves a trace. Crucially, we form memories of the past, not the future. This seems obvious, even tautological. But given the time symmetry of fundamental physics, it is actually surprising. Why should records point in one temporal direction? The answer is the same as for the arrow of time in general: the past hypothesis. The universe started in low entropy, and entropy has been increasing ever since. Records and memories are part of this increase. They are thermodynamic footprints of the past. This has a striking implication. Our knowledge of the past is not fundamental. It is derived from present evidence. We do not have direct access to yesterday. We have access to traces that yesterday left behind. Philosopher Bertrand Russell once posed a thought experiment. Imagine the universe popped into existence 5 minutes ago, complete with all the records and memories that suggest a longer history. How would you know the difference? You could not. All your evidence comes from the present state of the world. You infer the past from that evidence. If the evidence were created 5 minutes ago, your inferences would be the same. This is not meant as a serious hypothesis. Russell called it absurd. But it illustrates the inferential nature of our knowledge of the past. We do not perceive the past directly. We reconstruct it from present traces. Now connect this to the block universe. In the block universe, the past exists as surely as the present. Yesterday is really there, at its location in space-time. But you do not access it directly. You access it through memories, which are present states of your brain. This seems paradoxical. If the past really exists, why can you not access it directly? Why must you rely on fallible memories? The answer is that existence and accessibility are different things. The past exists, but you exist at the present. You can only interact with what is at your spatio-temporal location. Distant places exist, but you cannot reach them instantly. Similarly, distant times exist, but you cannot reach them at all. Memories are the only bridge. They are the only way information from the past reaches the present, carried by the continuous evolution of physical systems through time. This picture inverts our usual understanding. We think of the past as fixed because it has happened. The future is open because it has not happened yet. But in the block universe, both past and future are equally fixed, equally real. What distinguishes them is not existence, but accessibility. We have records of the past because entropy was lower in the past. We do not have records of the future because entropy will be higher in the future. The arrow of memory matches the arrow of entropy, not because the past is more real, but because thermodynamics makes the past more accessible. This has implications for how we think about changing the past. In science fiction, time travelers often worry about changing history. They fear that altering the past will create paradoxes or destroy the present. But in the block universe, the past cannot be changed. It is already there, fixed in the eternal structure. A time traveler visiting the past would find that their visit was always part of the past. They could not change it because there is nothing to change. What happened, happened. This is the self-consistency principle advocated by physicist Igor Novikov and others. Any closed time-like curve, any loop in time, must be self-consistent. The past the traveler visits is the same past that always existed, including the traveler's visit. This seems to limit free will. If you travel to the past, you cannot do anything other than what you already did. Your actions are constrained by consistency. But is this really different from the normal situation? In the block universe, your present actions are also fixed. You cannot do anything other than what you already do at every moment. The constraint on time travelers is just the general constraint on everyone, made vivid by the unusual circumstances. Let us return to the experience of memory. When you remember something, it feels like you are accessing the past. The memory seems to connect you to what was. You relive, to some extent, what you experienced. But physically, you are not accessing the past. You are activating a present state of your brain. The past is not transmitted to you. It is reconstructed from traces. This makes memory inherently creative. Every act of remembering is an act of reconstruction. You do not retrieve a fixed file. You regenerate an experience from fragmentary cues. Neuroscience has confirmed this repeatedly. Memories are not accurate records. They are reconstructions, influenced by current mood, beliefs, and context. Each time you remember, you alter the memory slightly. The past you think you know is shaped by the present in which you know it. This might seem disturbing, but there is another way to see it. Memory is not passive reception. It is active participation. You are not a passive observer of your past. You are a creator of meaning, constructing your history from the materials available. The past is real, in the block universe sense, but your relationship to it is dynamic. You engage with it, interpret it, integrate it into your ongoing narrative. The past shapes you, and you shape your relationship to the past. This is true regardless of metaphysics, but the block universe makes it vivid. The past exists eternally. Your memories are present reconstructions. The relationship between them is not transmission, but interpretation. Part 10. Final Reflections. We have journeyed through the physics and philosophy of time. We have seen that fundamental laws are time-symmetric, that the arrow of time arises from initial conditions, that quantum mechanics complicates our notion of a fixed past, and that the block universe treats all times as equally real. What should we take from all this? First, humility about our intuitions. The experience of time flow is compelling, but experience can mislead. Many intuitions that seemed undeniable have been overturned by careful investigation. Time might be another such case. This does not mean our experience is worthless. It is data to be explained. But it is not proof of metaphysical truth. The way time seems might not be the way time is. Second, wonder at the structure of reality. The time symmetry of physics is remarkable. At the deepest level, the equations that govern the universe do not distinguish past from future. This is not obvious. It did not have to be this way. It is a discovered feature of reality that invites explanation. Similarly, the emergence of time's arrow from initial conditions is remarkable. The low entropy of the Big Bang is not explained by known physics. It is a brute fact, a contingent feature of our universe that makes everything we know possible. These facts are worth contemplating. They reveal a universe far stranger and more beautiful than common sense suggests. Third, acceptance of uncertainty. We do not have final answers about the nature of time. The debates continue among physicists and philosophers. Different interpretations of quantum mechanics have different implications. Quantum gravity remains unsolved. This is not failure, it is the natural state of inquiry. We are pushing against the boundaries of understanding, and the boundaries have not yet yielded. Future generations may know what we do not. In the meantime, we can hold our views provisionally, remain open to new evidence, and appreciate the depth of the questions we are asking. Fourth, perspective on our experience. Whether or not time truly flows, you will continue to experience it flowing. Your memories will still feel like access to the past. Your anticipations will still feel like reach into the future. The present will still feel special, urgent, alive. Physics does not take this away. It contextualizes it. It places your experience within a larger structure that you can contemplate even if you cannot feel it directly. Perhaps this is the ultimate gift of physics. A view beyond the immediate, a perspective that transcends the limitations of direct experience. Let me end with a question. What if you could step outside of time and see the entire block? What would you see? You would see your life spread out in the temporal dimension. Your birth, your childhood, your present moment, your death. All equally real, all equally present in the structure of space-time. You would see that nothing is lost. Every moment you have ever lived exists eternally at its location in the block. The joy and the sorrow, the love and the loss, all of it is there, preserved in the fabric of reality. You would see that the flow of time, so vivid from the inside, is invisible from the outside. From the eternal perspective, nothing moves. Everything simply is. And then you would return to your temporal perspective, inside the block, experiencing flow and change and the passage of moments. You would know that this experience is partial, that it does not capture the whole truth. But you would also know that it is your experience, your way of inhabiting the structure of reality. Is the flow of time an illusion? Perhaps. Is it real to you? Undeniably. Both answers are true. Physics shows us a timeless structure. Experience shows us temporal flow. The two perspectives coexist, each revealing something the other cannot. Time flows backward, in the sense that the fundamental laws do not distinguish directions. Time stands still, in the sense that the block universe contains all times eternally. Time flows forward, in the sense that you experience it that way, right now, as you read these words. All of these statements are true, each in its own way. The nature of time is not a single puzzle with a single solution. It is a family of puzzles, approached from different angles, revealing different aspects of a reality that exceeds any single description. What should you believe about time? Believe that it is deep. Believe that it is mysterious. Believe that our intuitions, however compelling, are only partial guides. And believe that the investigation is worth pursuing, for its own sake, because understanding reality, however strange, is what conscious beings do. The next time you watch a clock, remember this. The ticking you hear is not the sound of time passing. It is the sound of a mechanism, vibrating at a regular frequency, governed by physics that does not distinguish past from future. The seconds you count are not units of flowing time. They are intervals of a constructed dimension, which your brain interprets as passage and flow. The future you anticipate is not empty and waiting to be filled. If the block universe is correct, it is already there, as real as the past, as present as the present. And the past you remember is not gone. It exists eternally, at its location in space-time, exactly as it was. What does this mean for how you should live? That is for you to decide. Physics reveals the structure of reality. It does not dictate the meaning you make within that structure. But whatever meaning you make it with awareness. The time you experience is not the time that is. The flow you feel is not the flow that exists. You are embedded in a structure vaster and stranger than intuition suggests. And that, perhaps, is the final lesson. Reality is not obligated to match our expectations. It is what it is, regardless of what we believe. The gift of science is seeing past our assumptions to the truth beneath. Time flows backward. Time does not flow at all. Time is the most familiar thing in the world and the most mysterious.